Okay. So let me go over that problem first, and then we'll go over problems from the last two most recent exams. So this problem is problem 10. And what it says is if f and g are bounded, measurable, and g is in L1 of Rn, with the integral of g being 0, and I define gk of x to be k to the n, g of k, x. The problem is to show f convoluted with gk goes to 0 almost everywhere pointwise. Okay, and so the way we end up doing this is, so you can use this little trick of, since the integral of this guy is 0, I can rewrite the absolute value of f convoluted with gk at x as being, after I apply triangle inequality, f of x minus y minus f of x. Gk of x dx over Rn. And so I think what I did last time is I split after this point, right? So I split it up. There's a region where I want y to be small, and then I can somehow use a version of continuity, L1 continuity of f, and the boundedness of g. And the part where y is large, for example, I use decay properties of g. But the trick here is I made a mistake where if I rewrite what k is, this is g of k, it's this guy, f of x minus y minus f of x. And this is g of kx. I'm sorry, these should all be y's, right? I'm convoluting. This is g of phi dy. Should be a y. Okay. And when I change variables here, so I let z equal ky. When I take dz of this, right, y is a variable with n real components, right? So this is k to the n dy. So in total, when I integrate this guy and change variables this way, any y becomes a z over k, and I can just replace this k to the n dy with dz. So this is going to be still over the same space, but I changed the one place where y is, it's x minus, and now it's going to be a z over k minus f of x. And this is going to be g of z. Okay. Everybody clear up to that point? What's happening? Okay, now I split. So I have the integral, and then here it's z is greater than, delta was a little bit misleading before because it's actually a large number that I'll need in this frame. So I split it up like this, g of z, dz, plus integral where z is less than r. Okay. So for this part, I'm going to use that that g is fixed. So use that f is bounded. Use f of x minus something. Yeah, these are all L infinity bounded. So 2 f and L infinity, right? So they're bounded function. And then I use this decay property of g. Right? And so since I'm taking a fixed function and I'm allowed to move around r, I can pick r large enough so that this whole thing, because g is integrable, is less than epsilon, right? So pick r so big such that this first term, so the integral z greater than r, g dz is less than, let's say, yeah, epsilon over 4 f in L infinity, right? So that makes this term less than epsilon over 2. Okay. Once I do that, I now fix this r, right? I've made this term small, and I want to use that g is bounded here, right? So here I need to use this, and then this guy is going to be z less than or equal to r still of this difference, x minus z over k minus f of x dz. Okay, so this term ends up being important, so let's copy it. And if I go through and start bounding this thing, what I end up getting is this guy is equal to, well, I change variables back. So I let w equals z over k. dw is 1 over k to the n dz. This guy is, when I do all the change of variables correctly, f of x minus w minus f of x dw. And then this interval means that, so z less than or equal to r turns into this guy, so that w is less than or equal to r over k. Make sense so far? Everybody following? Okay, cool. And so once I do that, what I notice is I can rewrite this quantity as being equal to, I'm going to write r to the n over r over k to the n. And then this is now a ball in the w variables around r over k. And this is an n ball around 0. And here it's going to be f of x minus w minus f of x w. I'm just rewriting things. And now I notice that, okay, if I group it like this, 1 over r, there might be some constant missing, but it doesn't really matter. So I have this part, r over k, 0, f of x minus w, f of x. So I know that this guy converges to 0 by the big differentiation term, right? As k goes to infinity. Because the diameter of this ball is going to 0, it's centered around the 0 point, right? So I'm averaging over, yeah, so part of the Lebesgue dominated or differentiation theorem says that this guy converges to 0 because I'm averaging over this ball. Okay, and so what we have is I have a fixed r, right? So this guy goes to 0. I can actually just show that the whole thing is going to be less than some epsilon, right? So that means that this guy converges to 0 actually uniformly in X. Not uniformly. This converges to 0 almost everywhere. Yeah, and it's not uniform because I don't know that this convergence is uniform, right? I'm at a different point X each time. These averages I can't control in any way. Okay, any questions about that? All right, wonderful. Yeah, I messed up. I think the main thing I messed up last time was I changed variables. I split apart this behavior too early. Really, you want to include this guy in somehow, right? I basically put all the behavior on G onto this. Okay, so that was that problem. Let's go and try some of the most recent exams. So yeah, I'll be working, let's start with spring 2022. And I'll just start going through the problems. So the first problem is the following. Assume I have a z in R, which has measure 0, and I define A to be the set of x squared such that x is in z. Show measure of A has measure 0. Okay, so the way you end up showing these types of things is I view this, let's write down what the function is, right? I write f of x equals x squared. A is going to be f of this set C, right? The great thing about f, though, is if I take a derivative, I know that it's 2x. So on any ball of radius r, so I guess this is, we're in one variable, so this is just negative r to r. What I have is f of x minus f of y is less than or equal to 2r times x minus y. Okay, and this, so what I'm saying here is in more formal language, f is locally Lipschitz. Okay, is everyone clear on how to show this inequality? So on, when I say on negative r to r, what I mean is x and y, for any x and y in this interval, I get this. Okay, so once I have this, let's look at z intersected with, not this way. I look at A intersected with BR, for R fixed for now. All right, so what I'm doing is I'm taking my big set, I'm truncating it because I have this inequality on this set. And what I get is the following. So what I want to say is any covering of my original set, Z, so Z is some subset of intervals, okay, with the sum being small, for example, being less than epsilon, since I know that Z has measure 0. What this shows me is I can get covering of A intersect BR, right? By just looking at IK squared intersect BR, K equals 1 to infinity. So this covers my set A intersect BR. Okay, so once I do this, now I know that the measure of this set, so IK BR, well, this is going to be equal to, it's going to be less than or equal to, let's say it this way. So IK is equal to some interval like AK, BK, right? Squared, which is the same as AK squared, BK squared, right? I'm just squaring. It's a continuous function, so it takes this interval to this other one. Okay. And because I intersected with, I'm looking at things which are intersecting with this ball of radius r, here I assume that AK, PK are in negative r. So when I get this, I get INK squared, and I use that this is less than or equal to, so this is actually going to be equal to b squared k minus a squared k, right? So this guy, so this is f of bk minus f of ak, right? Because f is just the square. Okay, so this guy is equal to f of bk minus f of ak, and I think I got to put absolute values. Okay. Okay, and so I know from my inequality that this is less than or equal to 2 times r, bk minus ak, right? But this is actually just 2 times r times this, the original interval. Okay, and so what we're going to use is I have it covers and I have a bound. So a intersected br is less than or equal to, by the monotonicity of the measure, the sum, k goes from 1 to infinity, of these guys, ik intersect br, which I know is less than or equal to the sum, k equals 1 to infinity, of 2 times r times ik. Right, is a really kind of brutal bound. But I know, okay, I move this guy outside. This is going to be equal to 2r. And in my covering, when I had an original covering, right, I just took any covering of z. Without loss of generality, I can assume that it's disjoint, right? Because if I have 2 overlapping intervals, I just make it 1 interval, right? So I can assume without loss of generality, this thing is all disjoint. So I get this. Okay. And this guy I know is less than 2r times epsilon. So when I take epsilon to 0, a intersect br is equal to 0. And this happens for any r, say greater than 1. What this implies is if I take a sequence of r's, right, I use the monotonicity of measure again to say that, okay, a actually has to be measure 0, right? By taking r to infinity.
Well, it seems like you could solve this a lot faster by using a change of variables argument.
How
Uh,
would you do this?
yeah, so we're integrating the characteristic function of a to get the measure of a, right?
Yeah.
So the characteristic function of a is less than or equal to the characteristic function of z applied to square root of x plus the characteristic function of z applied to
So
minus the square root
I
of
don't
x.
know if z is completely contained in the positive real numbers.
Well, right. But we have two terms. We have a one term for square root of x, and we have one term for minus square root of x.
Okay. So
And
I
then,
have square root of x. Yeah.
yeah, and then split those two up. You do a change of variables and get two integrals, but both of the integrals are integrating a function that's 0 almost everywhere. So both of those integrals turn out to be 0.
Mm. Mhm. Yes, but that involves some change of variables which are not scaling. They're nonlinear changes of variables, right? It's not
Right, but
translation, it's not scaling.
yeah, But as long as
So
it's a diffeomorphism from, say, well, one of them would be a diffeomorphism from zero infinity to zero
yeah,
infinity, and the other would be
but
a,
at the end of the day, when you're on this exam, you don't want to have to use things like you don't want to hit things with a big hammer in some sense. So in some like when you're looking at these things, often you want a more simple proof, actually. So there's an even simpler proof. Uh, I had this condition of locally Lipschitz. So it's a theorem in geometric measure theory that if I have locally Lipschitz things, I preserve Hausdorff measure in some sense. And so I could go that route, but there's an actually easier way to do this if I just look at this, for example. So if I look at this quantity, right? If I have some covering of my set, so there's an alternate way that's even simpler. So sorry. Okay, so the alternate way is if I look at ik squared, look at this measure, this is going to be, well, this guy, so it's going to be ak squared, bk squared, which is the difference of these squares, bk squared minus ak squared. And what you can end up noticing is that this is, it factors. So ak times bk plus ak. And if I know that bk and ak are bounded, this is less than equal to 2r, right? So this is, the whole thing is less than 2r times this guy. And really the whole point of the exercise is to show, so we've shown that when I take an interval, the simplest thing I know how to deal with, I get bounds like this. I can control one in terms of the other. Does that make sense? So it's like, I would think of it more like this instead of being extremely complicated. What's happening is any cover I get of my original set, which is small, turns into a cover of the other set in a bounded way. So that's when you're looking at these kinds of problems, it's often helpful to think of instead of going to change of variables. Then you have to deal with inverses and um, when can I actually do this? This one's kind of more from scratch. But good question. Any other questions about this kind of proof? Cool. The second, which one's better to you guys? I guess this proof, if I have any inequality like this, so any locally Lipschitz thing, it takes zero measure sets to zero measure sets. Um, but for this particular example of a square, you can end up just factoring and checking the same thing. So
yeah,
just,
I think I may have actually even seen the locally Lifshitz takes null
I
sets to
think it
null
is
sets on a
also
prelude, so that is
exactly.
a good thing to know.
Yeah. And the general argument is, okay, uh, this guy would be whatever the Lipschitz constant of your function is on a ball of radius r, right? So if you see that in problems, this shows that it takes zero measure sets to zero measure sets because it does it for intervals. Okay, wonderful. Let's go on to the next one. So this is still spring 2022, and this is going to be question 2. So if I have an f, which is a positive function, which may be infinite, going from Rn to these values, we want to show 2 things. One is the thing we've seen quite a bit already, which is Chebyshev. So show Chebyshev. And 2, if I'm integrable, f is in L1, then the set of x such that f of x is positive infinity has to equal 0. Okay. So for one, can anybody remember how to show Chebyshev? How about, let's see, Iris?
I remember you start with an integral of f and then you try to like get the other way.
So what should I
So
integrate? So I integrate something of f, right?
yeah, doesn't start with f and then I think you show that f is just measurable.
So if I integrate on this set, the set where I'm greater than or equal to k, what can I how can I bound this integral in some way?
It has to be greater or equal to the measure of that set times
Yeah,
k.
yeah, exactly. So I'm using monotonicity on this set, f greater than or equal to k, which is, so k is now a constant. This is now just the measure of f times k. And then if I rearrange, if I write this guy as less than or equal to the integral of f, because it's a positive function, so I'm only adding on more values, you get, so I divide by k, is this. So it's like a 2-line kind of thing. Okay, so that was pretty easy. What about 2? So in some sense, it should follow from 1, right? Because what's happening for 2 is I know that this set f equals positive infinity is equal to the intersection of f greater than or equal to k, right? So I'm only, the set where I'm infinity is the set where I'm above every natural number. So when I check this condition, so I know way back, if I take an intersection of things, right, and they're all decreasing, so these guys are all nested, I know that these sets AK are all decreasing. And when I take the measure of the first one, f greater than or equal to 0, this is equal to, greater than or equal to 1, say. This is less than or equal to, by Chebyshev, just the integral of f. So by monotonicity, of measure, of a big measure, what we show is that star implies the measure where f is equal to positive infinity is equal to the limit as k goes to infinity of these guys, f greater than or equal to k, which I know is less than or equal to limit as k goes to infinity of 1 over k times the integral of the L1 norm of f. Since I know this L1 norm is bounded, I get this is 0. Okay.
And you can also just directly use the definition of integration to show this pretty quickly.
You can also do that, yeah. But so another, I guess, an alternate way is the following. So if I look at this set, f dx, and I know this is less than infinity, I can bound f. I can do the same kind of argument, right? So if I integrate this guy, integral of f dx on the whole space is greater than or equal to the integral where f equals positive infinity, right? F dx, which is equal to positive infinity times the measure of the set f equals positive, which is either positive infinity or 0, depending on if this guy is equal to 0 or not equal to 0. So those are the 2 cases. I should flip them. So that's another way to do it. So there's two different ways to do it. This one kind of relies on, I don't know, I find this one a little bit clearer because it's dealing with finite numbers somehow. This one, you got this kind of condition where it's like, okay, in real analysis, when you're doing these things on the extended number line, I just kind of define these quantities to be equal to 0, right? So that's really what I'm using. It's kind of this notion. So there's 2 different ways to think about it. Okay, so that one was a really fast problem, right? Let's go on to the third one. So the third one in spring 2022. So this one's a bit odd. What it says is let f be, I'm going to use shorthand here. So this stands for bounded variation. And this is on this interval AB. So what it means is the variation, I take a partition of AB, right? And then I measure how far f jumped. I have to say that for every partition that I take, the sum over all of these jumps is finite. So my variation stays bounded. Then I assume f is equal to a g plus an h, where g is absolutely continuous and h is singular in the sense of functions. So h being singular means it's a continuous function and its derivative is 0 almost everywhere. Okay, so the idea is I assume this, I want to show that the integral of phi df, or I'll show what this means in a second, is equal to this guy. So this is a and b of phi g prime dx plus integral ab, this should be phi dh. So when I write these, I haven't talked about this much because it doesn't appear so often, in my opinion, on the exams. When I write this, this is what's called the Lebesgue-Stieltjes integral. Integration. And so the way we define this is kind of part of the exercise is, okay, what does this quantity mean? Is when I take, I look at df as being the measure, which assigns the following values. So if I look at an interval, let's say like x and y. So this, I'm viewing it as a measure, right? So what this should be is f of y minus f of x. And then I think I want to put, let's put this. Okay. So this is a measure, right? Which could be positive or negative. So f is not said to be increasing or anything. But as long as I'm bounded variation, I can actually define, starting from f, I can define df on intervals, which by the Carathéodory extension theorem defines a full measure on the interval AB. And so this integral here is the thing that comes from extending this measure to the whole space and then integrating some test function phi on the space.
So do we need to assume that h is a bounded variation here, or is it implied by the fact that it's singular?
It's defined by the fact that it's singular, I believe. Yeah, I have to go. We didn't really talk about singular functions. I don't think it's so important. You can look it up. So this is I should write this singular as a function.
Does the Cantor function have bounded variation?
I think they might. I think they have to be because if I can rewrite it like this. So f minus g equals h. And I know f is bounded variation and g is absolutely continuous, which implies bounded variation. So the difference is bounded variation. So I'm allowed to define this object, right? If I have this decomposition, because the space is linear. Okay, so that's how I define this guy. And honestly, in my understanding of this problem, if I was found this on the exam, I would do the following. So write down the definition, and then what you do is this induces, so what I say is this induces a measure, I'm going to call it mu f on AB, right? By extending this guy from being defined in intervals to the whole thing. So what I can do is I know that mu f is, yeah, so I can write mu f by the Lebesgue differentiation, decomposition theorem is this, by Lebesgue decomposition, where mu with these, this is absolutely continuous with respect to the Lebesgue measure. I'm gonna write it L. And this guy is singular with respect to the Lebesgue measure. So I'm connecting kind of these notions on being absolutely continuous on functions and singular on functions. I want to relate them to this decomposition. So one thing to note is that these guys are unique. So what this means is I can rewrite phi d, and then I'm going to write it like this, because that's what's happening, is going to be the integral of some function, and then it's going to be d plus phi d perp. Now, what I need to do is apply Radon-Nikodym to this guy. So what I'll get is some function. I'm going to call it g. Dun, dun, dun. Yeah, g prime. So you can check by uniqueness this holds. So if this is, so this is the Radon-Nikodym derivative of this measure with respect to Lebesgue measure. And so what this means is when I want to integrate phi against the absolute continuous part, I can write it as the integral of phi d. So this is the definition of the Radon-Nikodym derivative. This is the Lebesgue measure. The script L is the Lebesgue measure. And by uniqueness, you can check that this is true. So I don't know that originally, but I know it's true now. Okay, and there's some little argument to use uniqueness. And the same goes for the other part. If I write it like this, right, then I know that, okay, this actually has to be H. So uniqueness, I'm not going to go through the argument, but uniqueness of the decomposition gives our, gives, and then I'll label it. So this gives the statement here. Right, so what I've shown is, okay, I integrate mu with respect to d mu f, it's the same thing, I'm just calling it a different thing. And then I know that I can separate d mu f as two parts. There's an absolutely continuous part and a singular part. And actually, by uniqueness, you can check that g prime has to be equal to the Radon-Nikodym derivative of the absolute continuous part. And this singular part actually has to correspond to H. So this singular part. And it's just kind of unwinding the definitions of those. Okay, so give star. So the way I would view this problem, I mean, this is just a lot of words, but I think it would be absolutely fine to write this on an exam, because really what it's checking for is, do you know the definition of absolutely continuous and singular? Do you know the definition of a Lebesgue-Stieltjes measure? And do you know Lebesgue decomposition and Radon-Nikodym? That's really all the problem's asking you. And if you wrote down this, I think you would get full points, right? Even though all the steps aren't there.
So do we need to so we show this for intervals and then we apply to uniqueness of the extension to show that for measure? Okay, so we're doing that.
Yeah, in some sense to get this. So the way you define this object in the first place is so Lebesgue-Stieltjes integration starts with, okay, I can only define this guy on intervals, right? Because I'm defining it as a difference of two things. And so in order to create the full measure, I'm using a extension theorem. So that's where I'm using it to actually define the object. And then the rest of it is just applying measure theory results to and using uniqueness at this decomposition.
So in an exam, like we don't like in this problem, we never need actually to appeal to the definition, like to work with intervals. We can just work with the whole measure.
I don't think so. You know, it like if you did this, it would
I
show
was
to me.
thinking-
If I was grading this exam, it would be like, you know what's happening, right? So this this part would be nice. You could probably write a little bit more about this, like, oh, it induces a measure by Carathéodory, for example.
Because I was thinking that when you need to use that G is absolutely continuous as a function, and
Yes.
then the fundamental theorem of calculus for absolutely continuous functions, and you can show that the integral from A to B of phi G prime is the same as the absolutely continuous measure only on intervals, and then by uniqueness they're equal on the intervals, but then you need to apply to use the extension to
Yeah, that also works. That might actually be a simpler, more conceptual way to view this thing, where I work on intervals and then I use my decomposition to show certain properties, right? And I think even in this particular scenario, do you still use this decomposition theorem, or you just okay? Yeah, so this is how I would do that problem. That way also seems reasonable. Where you work on intervals.
Thanks.
Okay, yeah, for sure. Okay, so this one to me somehow kind of definition checking. Let's see. Let's go to the next one. So this one, 4, says I take a sequence, sorry, of FKs, which are all positive or non-negative, and they go from some domain E in Rn into positive numbers, right? And I know that, so I know Fk converges to F and Fk less than or equal to F almost everywhere. Show that the integrals converge. So the one thing you should know about these problems, if I don't have any notion of L1, things being in L1, I can't expect to apply like bounded convergence theorem or dominated convergence. So really the only tool that I have is Fatu. So because I have no control from above, right? So dominated convergence says, okay, there's some finite envelope of this class of functions I'm considering where everything will work. This, I don't have that, but I have non-negativity. Okay, so you may have seen this. This is called the monotone convergence theorem. If you've read Calderon-Zygmunt, sorry, Whedon and Zygmunt or something like that, or Stein's book. Okay, but let's show it. So proof assuming Fatu. So if you remember how to do Fatu, this can be done directly, right? But I think it would be okay to assume Fatu. So what do I know? So I want to look at the integral of f, but I know that it's the pointwise limit of these guys, right? So this is the limit of fk's. Okay, these are all over the set. Now Fatu tells me, okay, I can get this guy less than or equal to the limit of integral of e of k. Okay, but I also know that the lim inf is less than or equal to the lim sup of these integrals. So these are real numbers. And I can use the monotonicity of, so fk is less than or equal to f for every f. So for every k, right? So when I integrate these quantities, I get a less than or equal to. So this guy is less than or equal to the lim sup, k goes to infinity, of integral of f, right? Because they're all bounded above. Okay. Which is equal to integral of f. So I know that all of these guys are squeezed together, right? Because there's an f on the left-hand side less than or equal to f on the right-hand side. So in particular, what this shows is that lim inf of integral of fk equals lim sup integral of fk, which equals integral of f. So that shows that the limit exists because the lim inf coincides with lim sup, and it's actually equal to integral of f. Okay, so really the only hard part we used was this one. So fatu is used here. The rest are just lim sup, lim inf, taking the limit of a constant sequence, etc. And then monotonicity. Okay, any questions about this? Okay, let's do the last one. Yeah, let's do the last one in spring 2022. So this is problem 5. Here I have, it's an LP-LQ problem. So I have P and Q, which are conjugate exponents. And I have a function f, which is an LP of Rn, and G, which is an LQ of Rn. Show f convoluted with G, bounded, and continuous. Okay, and we may have done this before, I forget, but let's go through it again really quick because these convolution things show up very often. So let's first show it's bounded, right? So I have to control this quantity by something uniform. First, I write out the definition of convolution and then apply triangle inequality. So this is f of x minus y, g of y, dy. Now, what I can do is I apply Holder with LP and LQ. So this is f of, and then it'll be a x minus dot, and this is LP, and then g and LQ. All right, so this is Holder. This holds through any LP and LQ. And I know that LP spaces are like translation invariant, right? So this is actually equal to F and LP, G and LQ. Since LP translation invariant. Okay. So I know by my assumption that they're in LP and LQ that this is finite. So I'm good there. I've checked that it's bounded. For the other part, I need to be a little bit more clever. So here's where I need to start caring about exponents. So without loss of generality, let's assume that P is not equal to infinity for the moment. So the norm that I'm measuring F in is not L infinity. Then when I want to look at this difference, G of X minus F convoluted with G of Y, I do definition of the convolutions and triangle inequality. I get this is less than or equal to the integral of f of x minus z minus f of y minus c, g of z, dz. Okay, and so for this one, I write this in LP and LQ. I do Holder again. And this is f of x minus dot, f of y minus dot, LP, G, LQ. Okay, and because I'm in LP, I can change variables. So for P not being infinity, I can also do it for P equals infinity, but let's call W equal to Y minus Z, right? Then dw equals dz. And I have z equals y minus w. So when I replace this, when I change variables like this in here, this guy is actually going to be equal to f of x minus y minus f of this LP GLQ. Okay, and so this is a translation by this vector x minus y in RD in Rn. So so we know
You should add x minus y plus dot.
I think it might be, yeah. Let me think. Because it should be there's a minus. Yeah, I think this might be plus. Yeah, but the whole idea is I have a function, right? And let's say some bump like this. And if I just take it and translate it, right, by some small vector, then this difference is going to be small because I'm measuring an LP. So I know that translation is continuous in LP for P not equal to infinity. So at the end of the day, when I look at this difference, I know that, okay, if I take x and y close enough, right, this quantity should go to 0, which shows that, okay, that the limit as x approaches y of this quantity equals 0, which shows I'm continuous. Okay, so if I do that, what about P equals infinity? What do I do in this case?
You just swap P and Q.
Yeah, yeah. So I know if I do convolution like this, I know that it's actually equal to G convoluted with H on LP spaces, LP of Rn. Right? So I should just say on Rn. Okay, because I'm translation invariant. So if I do this, if P equals infinity, Q, which is the conjugate exponent, equals 1. So flip argument with F and G. Okay, and so that takes care of every case because I needed to include the case where m equal to infinity. Okay, and so actually that's the first exam is these 5 problems. I think I'm going to go over one more problem. Let's see.
So in this last question, the way you show translation invariance is through approximation by continuous functions?
Yes. Yeah. So you approximate things by continuous functions.
You
And
might
then
need continuous and compactly supported just to
I was
make
about to
everything
say,
super nice.
yeah, you first maybe intersect it with a ball, like a finite ball, like some large radius. Then I'm in some finite domain, and then I use continuity of functions. I think you could just say that continuous functions are dense in L1, right? And that will get you, okay, I can approximate these guys. So they're dense in LP for P not equal to infinity. And then similar argument holds, right? That's basically the only reason why this guy fails to go to 0 when x approaches y in P equals infinity. Because in L infinity, I cannot approximate things by continuous functions, right? If I take a characteristic function and then try to approximate it by some sort of continuous function, no matter what, there's always going to be some sort of jump. So on some small measure set, the difference is 1. It's going to be large. So that's why that doesn't work. Okay, yeah, so continuous, you show this statement by approximating continuous functions. Okay, let's do one more. So this is the first problem of last year's exam, which I thought was kind of cute. So I look at a p between 1 and infinity, and I take a f and a sequence fn, which is an LP. And I assume that I know that fn converges to f almost everywhere, and fn is less than or equal to m for all n. So prove, so these are assumptions, assume. Prove for every g and LQ, so the dual exponent to p, that I have a weak convergence. So these guys converge. So this often is written that f converges weakly to f in LP. Okay, so the way we do this is the following. So first, so fn converges to f almost everywhere, implies that there exists some small measure set, z is less than epsilon, and fn minus f is less than eta on z epsilon complement. Right, so this is Igorov. So pointwise convergence of measurable things is almost, it's like up to some small measure set uniformly convergent. So I know this first. Let me think. Do I even do that? Okay, cool. Yeah, and so what we'll need to do in order to control this quantity is I write the integral of this times g, take its absolute value, right? So I need to control this quantity. The way I do this is I break it into two sets. So there's going to be a set on z epsilon times g plus, and then the interval 0, 1 minus z epsilon, or z epsilon complement. So on the set where I'm, let's call this 1, let's go 2. On 1, I know that, okay, this is a set of small measure, right? So if I do Holder, this guy is less than or equal to fn minus f in LP, g in LQ, and each of these is on z epsilon. Right? Okay, and I know this guy is less than or equal to fn plus f on the whole space. So on P. But I know that by this is less than or equal to 2m, where m is this guy. So actually, you can show that this should be in P. And the reason you do this is, you can show this, is I know that f in LP is less than or equal to, by Fatu, the limit as n goes to infinity of fn LP by Fatu. Sense. Okay. And for this term, right, so G in LQ of Z epsilon, I know that how do I say this? This guy goes to 0 as epsilon goes to 0. Where this is the measure of the set, right? Because I'm shrinking on this set. The way you do this is so by dominated convergence. Applied to, and this should be G characteristic function of Z epsilon, which converges to the 0 as epsilon goes to 0. And I know that G of this guy, Z epsilon, is less than or equal to G. So if I take the pth power, or the qth power, is in L1. Okay. So what I've shown is that this guy goes to 0 as epsilon goes to 0. Okay, so pick epsilon small enough so that this guy is less than like your error tolerance. For the other part, so this was the part where I'm on the small measure set, Z epsilon. On the part where I'm on the main chunk, I used Egorov to show that these guys are uniformly convergent, right? So I get that for 2, I'll write it out. This is the integral on Z epsilon complement of Fn minus F G dx, which is less than, I called it some eta, but the integral of G over Z complement. Okay, and so what I do is I formally put in a 1 dx here, just the number 1, and I apply Holder. So I get eta, and this should be G in LQ. And when I take the integral in LP of the function 1, right, I get, okay, that whole integral is going to be the integral of just the set over the set, this guy, of 1, right, 1 to the p, for example. And I'm taking 1 over p. So when I reduce this, this is going to be G LQ of the measure of Z epsilon complement to the 1 over p, which is less than or equal to 1, since I know that this whole thing is in 1. So this is eta times G. So the order of picking all of these things is pick epsilon such that 1 is less than eta, and then pick, yeah, okay. Then what it shows is 1 plus 2 is less than, it should be eta plus, so eta times this norm G plus 1. Okay, which goes to 0 as eta goes to 0. So here again, I'm splitting the integral in between 2 behaviors. The 2 behaviors are when I uniformly converge, is just on a large set, and then when I don't have any control on that, but I'm on a small set. So I split the argument those 2 ways. Okay, and I think that's all I have time for today. Any final questions about this problem? Okay, well, great. Well, it's been great having you guys. I wish you the best of luck on the exams, and I'll upload these last 2 videos on the internet soon. So best of luck. Yeah,
It's hard to believe this is our last time.
Well, hopefully it was you've learned something.
Definitely, yeah.
Thank you.
For sure. All right. Thanks, guys.
All right, hopefully
Um,
I'll see you around. Well, will you be around in the fall?
So I'm actually, I don't know if you could see,
Or
but
wait, you
I'm about to move out to Sanford. I get the truck today. So
well, congratulations and good luck. Yeah, I couldn't
thank you.
remember if you were the one who had already graduated.
Yeah, yeah, yeah.